the title that I'm talking about is Dynamic Agroecological Classes, Assessing Land Use Change. And when we first started the project, we started discussing agroecological zones, and I wanted to thank all the people that have joined in the discussion and have been often patient from the standpoint of changing names and what an AEZ is or an AEC and what the difference might be. And so we've had really good conversations over the course of the project from the standpoint of this whole concept of agroecological classes. And, you know, the more traditional definition of agroecological zones is basically dependent on the drivers. It's the climate, it's the soils, it's the physiography that shape what an actual zone might be. And with this project, we took a very different approach, exactly the opposite approach. We started to take a look at what the actual expression of land use was on the ground itself. In other words, the result of not only the biophysical drivers, but also the social economic drivers that result in, okay, what is actually produced on a given piece of land? And to use that then as a basis for classification. So here we are, dynamic agroecological classes, and the purpose was foremost to establish land use baseline and the capacity to evaluate shifts in land use over time. How do we do that? How do we actually assess how much diversity we may be seeing in the landscape now, and if there's going to be future intensification or not, how do we even know that? And from that standpoint, if you look at our dryland systems, you can divide our current cropping systems into three fairly easy classes based on the proportion of fallow. That's grain fallow, where we have annual fallow and then winter wheat mostly. And then we look across the region, and as precipitation increases, we start to see fallow start to decrease. And annual crop fallow transition uses a little bit less fallow. And then annual cropping is where we've basically tried to eliminate fallow, or fallow is really restricted. And also, in addition to just following land use and land use dynamics over time, we also want to establish a geospatial land use context for research, education, and outreach activities. In other words, where are the products of REACH most relevant from the standpoint of our region? Where can they be directed towards where they're most contextual from the standpoint of being relevant for that particular area? So we're assuming that agricultural systems and land use have emerged as a consequence of biophysical and social economic drivers. Three major AECs were defined: annual cropping, less than 10% fallow; annual crop fallow transition, 10 to 40% fallow; and then grain fallow, greater than 40% fallow. And we could use the information that comes from NASS, the National Agricultural Statistical Service, produces a cropland data layer, and I've displayed this on the left, and there's where we are. It kind of looks like an amoeba to me, Sanford. I'm not sure about the stain in your sink, but this is kind of, it's a little bit of a, or maybe it's a flea. But anyway, a Daphnia, that's what it looks like. You're right, it's a Daphnia. But anyway, this particular land use cover classes identifies on a 30-meter basis what the actual land use was, whether it was in winter wheat or spring wheat or canola or grass or something, or forest or something else. So from that standpoint, then, we get a map like this every year that shows us what the land use was for that given year with fairly good accuracy. And so we started to see, or tried to look at, how we could use this type of information to derive the major AECs that you see here. And basically what we did was look at each pixel, 30 meters again. We looked at the pixels around it to see what the different kinds of crops were in the proportion of fallow, and we used that information basically to classify it into one of these major, three major AECs. So that's what the map looks like. If you start to accumulate years, then you can see if the classification for a given pixel remains the same. We've identified that as being a stable situation, or if the classification changes over the course of the years. So if that classification changes, we're calling it a dynamic agroecological class. But if it didn't, then we're calling it a stable agroecological class. And so here we have the green that you can see here as annual cropping. And the annual crop fallow transition, as in this darker yellow, and the grain fallow in the brown. We've also showed the irrigated that here we're not dealing with that today. And then the dynamic agroecological classes you can see kind of occur in transition between these stable areas. So you'll see that this darker yellow is transitioning into an annual crop fallow transition that's more dynamic, and then into an annual cropping situation that's also more dynamic. And so this is telling us that growers are responding to certain circumstances for that particular year in terms of what they're growing and the crops, et cetera, and whether they're using fallow or not. So from that standpoint then, this starts to identify spatially, geospatially, where certain kinds of cropping systems occur, and also where there's more dynamic from the standpoint of, in this case, the use of fallow and the proportion of fallow. So we started to ask the question, can we actually explain the variability in classes that we see across the region using bioclimatic variables? And the intent here was if we could use bioclimatic variables to actually explain the variation in classes that we see across the region, then we could use predictions using global circulation models. We could use predictions of future changes in bioclimatic variables to actually see if we were to impose those changes on current situation in terms of technology, et cetera, what kinds of shifts we might expect. So this was a question that was headed up by a doctorate student of mine, Harsimran Kaur, with lots of help from many of you in the audience. We're using a random forest, which is an empirical statistical model. So this is very different from Dr. Stockel's modeling, which is more of a process-oriented type of simulation process. This is very empirical, which means cause and effect can be questioned at times. You're always trying to decide what cause and effect might be from that perspective. We used 44 different bioclimatic variables that are important for Mediterranean kinds of climates. So these are bioclimatic variables that have been identified as being important in our particular climate for the biology that we see expressed. And using all 44 of those bioclimatic variables, the overall model accuracy for basically predicting where these different classes would be, explaining the variability of those classes, was about 76%. Not bad for just bioclimatic variables, remembering that, again, the land use is expression not just of biophysical kinds of drivers, but also social economic drivers. So from that standpoint, we were actually pretty pleased that by just using bioclimatic variables, we can see that there's quite a bit of accuracy in terms of classifying where those classes would exist, the AECs, just given these bioclimatic variables to predict that. And then we backed up and said just using it's difficult to actually predict or to interpret 44 different bioclimatic variables all interacting, et cetera. So it's a little bit easier to see if we can't look at just a few of those bioclimatic variables, and we could use just 3 bioclimatic variables to explain about 69% of the variability. So we're not doing so bad there. And so those 3 were the Holdrege evapotranspiration index. This is basically an index of evapotranspiration. Again, Holdrege developed one that's kind of pointed towards biological systems, and you divide the ET, the potential ET, by precipitation. That gives you this particular index. And that was the most important variable from the standpoint of explaining some of the variation. The spring precipitation was also important. That's March, April, May, cumulative precipitation. And then the precipitation during the summer months, basically, as well. And again, a model accuracy of about 69%. Not bad, using just 3 variables. And so this is the Holdrege evapotranspiration index. And in this case, we've outlined where it's 1. And we've overlaid it on top of the current AECs. And you can see that, and we chose 1 simply because 1 is the index where, and less than that is where we would expect to find, and Holdrege would expect to find annual cropping to occur. So as you get larger than an index of 1, that's where we start to creep in more fallow. That would be predicted from this particular index. And so here we have an index of 1. And you can see that it kind of follows. Here's the annual cropping in green again, and going around and forth a little bit hard. And we'll just concentrate on this upper portion. Here's 1.5. So here we are kind of splitting where the annual crop transition and the grain fallow particular AECs are. Again, just using one particular index. So from that standpoint, you can take that, and we've applied then future global circulation model predictions or projections of how that index might change. And if you look at the 2070 scenario using 19 global circulation models and the representative concentration pathway of 8.5, that's what the shift is. So the little dotted lines here show a shift to where 1 occurs. So in other words, this would be saying that the annual cropping acreage is shrinking. And furthermore, if you look at the 1.5, you see that the line is now shifted to the east, and this is saying that our grain fallow is going to start to replace some of our annual crop transition, and our other AEC, the transition AEC, is starting to creep into more of the annual cropping. So this is just one of the variables and how you might go about interpreting that. And so if you were to look then at future projections of bioclimatic variables and impose those on top of the current situation, what would happen to our current AECs? And this is the map that shows that. Here's our current AECs. It's on a 4x4 kilometer grid. And the arrow up here is showing what that shift might suggest from the standpoint, again, of just using bioclimatic drivers, these three. And you can see the upshot of all this is that the amount of more dynamic AECs increases tremendously, whereas our stable AECs tend to recede in terms of the amount of acreage that we see. And also that we find more fallow involved in terms of the AECs, in terms of their shift. So here's our AECs again: annual cropping, stable and dynamic, AEC transitional, and then grain fallow over here, stable and dynamic in each case. Now, the current situation in millions of acres, and then 2070 again at the representative concentration pathway of 8.5. And you can see the big winners are AC transitional in terms of being dynamic, as well as the grain fallow dynamic. So again, the dynamic classes through here, the central portion of the region, increasing from the standpoint of acreage. The losers being the annual crop dynamic and the grain fallow stable. And so the interpretation of this then is more dynamic agroecological classes in terms of how we've classified them, more use of annual fallow, which is disturbing from my perspective and probably others as well, which means less cropping intensity, greater erosion hazard, and also a decline in soil organic matter. And then future research efforts really, I think, are in tune with what's been discussed already, that we have been discussing. Greater use of flex cropping. Flex cropping is where we actually take the current situation from the standpoint of the kinds of weather, moisture, et cetera, that we receive at a certain point, at a certain decision point, and we decide, should we annual crop or should we fallow? So from that standpoint, or should we choose a different kind of crop, maybe canola or peas or wheat, or should we fallow? So flex cropping starts to look at a much more dynamic system in terms of assessing what the current weather has brought us and what should we do from the standpoint of a decision-making standpoint in terms of this next year and growing a crop. Increased winter cropping, question, and then the soil health considerations are extremely important here from the standpoint of working on how the health of our soils may be changing, particularly soil organic matter, and impacts of these kinds of predictions on soil organic matter, and monitoring and having the measurements and tools available to growers to monitor changes that might be occurring in their soil health. So current and future research, we hope to continue to work with Dr. Stockel and others from the standpoint of incorporating CropSyst into the flex cropping question in particular. In other words, can we use the simulation models effectively to combine with our AEC designations to go forward with better decision support in a flex cropping situation in order to better make decisions? And I think this is an area that we're working in right now from the standpoint of improving decision aids. But also, these kinds of models provide us with much more information from the standpoint of ecosystem services. What are the other outcomes from the standpoint of making a choice of growing a crop? And I want to mention then also the creation of the national USDA LTR Network. This is a picture of the 18 current sites. We're over here. We're one of the first 10 that were identified. And this, as Sanford alluded towards, in moving towards the future, is going to be one of the platforms that's going to have to rely on all of you that are here and the teams that we created that actually made us look really good, and why we were selected to begin with. It was this partnership that helped to create the LTAR that we have established now at Cook Farm. And its continued success is going to be dependent on all our efforts here and around. So, I'm done.